Welcome to another Mathologer video. Liouville's number, the monster up there, consists of infinitely many isolated islands of ones at the 1 factorials, 2 factorials, 3 factorials, etc. digits, with exploding gaps of zeros between them. As I promised you at the end of the last video, today's mission is to show you a nice visual way of seeing that this number is transcendental. I'm pretty convinced that as far as transcendence proofs for specific numbers goes, what I've put together here is as simple and as accessible as it will ever get. Still, if you make it to the end and understand all my arguments, I think you can be pretty proud of yourself, since not even that many professional mathematicians know any transcendence proofs. And if you make it to the end, I've got a special treat for you. I'll show you how you can use Liouville's number as a template to make a clone of the real numbers within the real numbers. This clone is made up of transcendental numbers, like this strange cousin of pi. But perhaps the craziest thing about this clone is that although it is as large as the set of real numbers itself, it is of measure 0. This means that, in a sense, it takes up no space within the real numbers. For those of you in the know, this set is closely related to Cantor sets. What's a transcendental number again? Well, for a detailed introduction, just watch the last video. So here, just real quick. The transcendental numbers are defined in terms of what they are not. They are not among the real numbers that you encounter when you're doing classical algebra, like the integers, the rational numbers, any of the real numbers that can be written as Ricci expressions like this, or any of the real numbers that pop up as solutions to polynomial equations with integer coefficients like these. This last set of numbers is called the algebraic numbers and includes all the other types of numbers that I mentioned before: integers, rationals, and Ricci numbers. Anyway, we call a real number transcendental if it is not algebraic, if it is not a solution of any polynomial equation with integer coefficients. Liouville's number, or Liouville's constant, was shown to be transcendental in 1851 by the great French mathematician Joseph Liouville. It was one of the first numbers shown to be transcendental, and Liouville's proof of this fact is probably the easiest transcendence proof for any specific number. Liouville's proof is accessible to anybody who has had some exposure to proofs at university level real analysis, and I've included links to the original French paper and a modern version of the proof in English in the description. But since many of you would struggle with any of the proofs in these papers or in textbooks, I've tried to come up with an alternative way of seeing the transcendence of Liouville's number that can be understood and hopefully also enjoyed by anybody who watches these sorts of maths videos, including all Mathologer fans who are still in high school. I'm still working on the primary school version, but I'm probably never going to get there. Okay, Liouville's number. Lots and lots of zeros and ones, and the ones are the 1 factorials, 2 factorials, 3 factorials, etc. digits. Just a quick reminder, 1 factorial is equal to 1, 2 factorial is 1 times 2 is equal to 2, 3 factorial is 1 times 2 times 3 is equal to 6, 4 factorial is 24, then 120, 720, 5040, etc. A sequence of numbers that grows rapidly, which means that the stretches of zeros between consecutive ones get longer and longer extremely quickly. Okay, here then is my proof that Liouville's number is transcendental. Let me know in the comments whether this proof works for you. When dealing with a complicated number like pi, approximate value often suffice or are at least a good place to start. To get such an approximation, we often chop off the decimal expansion at some point. Now let's approximate the number pi squared with the squares of these truncations. Then these approximations for pi squared will be spot on up to a certain digit, and maybe good enough for some application we have in mind. However, from some point on, these approximations all go off target. For example, the last approximation down there coincides with pi squared in only the first 4 digits, and the remaining digits that you can see here are wrong. Liouville's number L behaves quite different in this respect. But to start with, the only distinguishable truncations are those that cut off after the ones. And these are the first 4 of these truncations of L. Now squaring gives these numbers here, and in contrast to what we had before, all the digits of the square truncations seem to be correct. And looks are not deceiving. This is actually always true. And the reason for this is not too hard to pin down. It's because all the non-zero digits of Liouville's number are spaced further and further apart, and those further down the line simply don't play any role in producing the earlier digits of the square of our number. For the moment, I'll gloss over the technical details, but I'll return to them after I've finished outlining the proof. Anyway, what happens if we raise L to a different power, say 5? Well, then, as you can see, while the approximations are still definitely damn good, things are no longer spot on for all digits. Here, for example, 1 digit is wrong, and here, 3. But if you look closely, you find that the next approximation is spot on again. All digits are correct. And actually, things will be spot on from this truncation on. So all digits of truncation L5 to the power of 5, L6, and so on will be correct. In fact, something similar will be true for all powers. So, as we've seen, all squared truncations are spot on. The same turns out to be the case for the cubed ones. 4th powers too. 5th powers, we've already seen that all digits are spot on from a certain truncation on. Same thing for 6th powers. Except this happens a little bit later, and so on for all powers. Now we find that the same is true if instead of just powers, we look at any polynomial with positive integer coefficients. All pluses, no minuses there, right? So if instead of just powers of the number L, we're approximating a polynomial like this, evaluated at the number L, then we find that all the digits of our approximations will be correct from some truncation onwards. In particular, in the case of this polynomial, all digits will be correct from L2 onward. We're getting pretty close to the punchline. Remember, what we have to demonstrate is that L does not solve any equation like this. To get the proof going, we first move all the negative terms to the right side. Now this results in 2 of those special polynomials that only have positive terms. One on the left and one on the right side of the equal sign. Now let's assume that L actually is a solution of this polynomial equation. This means that the number on the left of the equal sign is actually equal to the number on the right. I'll call this number the number at the top. Now let's see what numbers we get on the left and right when we replace L by one of its truncations. Let's start with L1 and work our way up. Obviously, the higher the truncation, the better approximations to the number at the top we'll get on the left and on the right. But we also know that in addition to this, all digits of these approximations will be correct from some truncation on. For the sake of the argument, let's say that this is the case from L5 onward. What this means is that now the first digit of the approximation on the left is equal to the first digit of the approximation on the right. The second digit on the left is equal to the second digit on the right, and so on for a while. Until, well, you'd expect one of the 2 sides to run out of non-zero digits and the other side to keep on going before it stops too, right? And maybe that's exactly what will happen. However, surprisingly, and we'll see why when we go all technical, at this point, our assumption that L solves the equation also implies that starting with a possibly higher truncation, let's say L6, we will always run out of non-zero digits at the same time in both approximations. So this means that our 2 approximations are in fact equal from this truncation onward. And this means that just like L itself, L6 and all the following infinitely many truncations are also solutions to our polynomial equation. But infinitely many different solutions are impossible because the polynomial equation can only have as many solutions as its degree. For example, our degree 6 polynomial can have at most 6 solutions. And so the assumption that our number L solves a polynomial equation with integer coefficients leads to the absolutely impossible conclusion that this polynomial has infinitely many solutions. And this means that our assumption that L solves an equation like this, was wrong in the first place. And that means that L is a transcendental number. Very neat proof by contradiction, right? Of course, what I did not show you is that all the approximation will eventually be spot on, no matter what polynomial equation we're dealing with. Okay, so let's have a closer look. So the different ones in our number L just stand for different powers of 10. For example, the first one stands for 10 to the minus 1, the second for 10 to the minus 2, the third for 10 to the minus 6, and so on. And the number L is just the sum of these powers of 10. Now we started by pondering L squared, so let's have a look at how we would calculate this number here. Actually, before we do that, let's calculate the square of the second truncation. Okay, so here we have to multiply every term at the top with every one at the bottom and then add up. So 10 to the minus 1 times 10 to the minus 1 is 10 to the minus 2. 10 to the minus 1 times 10 to the minus 2 is 10 to the minus 3. This times that, 10 to the minus 3 again. This times that, 10 to the minus 4. Add up everything to get the square we're after. For L squared, we have to multiply again every term at the top with every one at the bottom and then add up. Yeah, might take a while, right? So 10 to the minus 1 times 10 to the minus 1 is 10 to the minus 2. Minus 1, minus 2, minus 3. Minus 1, minus 6, minus 7, and so on. Minus 2, minus 1, minus 3, minus 2, minus 2, minus 4, and so on. And so on. Now, why are the digits of the squared truncation correct? Well, its rightmost digit, 1, comes from multiplying the rightmost term of the truncation with itself. For the other terms to interfere with the digits of the squared truncation, one of the terms outside the box at the top, multiplied with one of the terms at the bottom, should be at least as big as 10 to the minus 4. But the largest number we can make this way is 10 to the minus 6 times 10 to the minus 1, which is 10 to the minus 7. A lot smaller than 10 to the minus 4. Okay, so there's no danger here. What about these critical numbers for the next truncation? Also no danger. And the gap between the exponents minus 12 and minus 25 is larger than before, so even less danger. One more. The gap has increased even further. Now it's a one-liner to show that this trend continues. And I actually leave it to you to sort out the details. And well, actually, you only get partial credit if it takes you more than one line. Let's have a look at all this for the fourth truncation of the fifth power of L. That's the next thing we looked at, right? As I said before, all digits are correct for this fourth truncation. Let's double check this. Yes, the green 124 is larger than the yellow 120. Tick. Again, I'll leave it to you to fill in the details to show that this will also be the case for the higher truncations. Remember that there were problems with the lower truncations. Let's see where these show up here. Okay, the order has flipped. The 30 is now larger than the 28. And so there will be wrong digits in the approximation. One step down, there's also trouble with the green terms interfering with the digits of the power of the second truncation. Okay, so here are the first digits of L squared. I'd just like to highlight again the gap between the yellow lowest terms of the squared truncations together with the corresponding worst case scenario green terms. As we've already observed, this gap is increasing. In fact, it will get arbitrarily large. And the same is true for all the other powers once the gap starts appearing from some truncation onward. Those of you who did those one-line calculations earlier on will already have convinced yourself of this fact. Okay, now, what about polynomials with positive integer coefficients? Well, they're built from powers. Take, for example, L squared plus L. Highlight the second truncation. First note that the corresponding green digits are basically aligned. That's because the top one essentially comes about from multiplying the bottom one by 10 to the minus 1. That's a shift of one position. Anyway, this relative alignment will always be the same as we move to the right. Also, as we move towards the right, the gap of zeros in front of the green digits gets as large as you wish. Given this gap of zeros, it is clear that when we add up L3 and L3 squared, none of the green digits or beyond will add to the sum within L squared. And so the digits of the approximation will all be correct. But what happens if the individual powers in the polynomial are multiplied by non-trivial constants? For example, let's multiply the linear term by something huge, say 10. The overall effect of this changed term are its non-zero islands possibly growing and the greens shifting to the left. This may lead to the overall gaps in front of the greens shrinking or even vanishing for really large coefficients like googolplex. However, since the gaps grow unlimited in size, they will eventually absorb the shrinkage and gaps will always be present from a certain point on. And this means that no matter what polynomial we are dealing with, all our approximations will be spot on from a certain truncation onward. Almost there. In the final part of the proof, we assume that L solves a polynomial equation like the one up there. I claim that this implies that from a certain point onward, all truncations also solve this equation, which then gives the contradiction. Well, as just now, we can see that from a certain truncation, say L5 onward, we have the usual common gap of zeros for all the terms in this equation. But then, for the identity on the left to be true, which is our assumption, the sum of the two approximations on the top must be equal to the sum of the two at the bottom, which is exactly what we needed to convince ourselves of. Anyway, that's basically it. Of course, I could still fill in all the nitty-gritty calculations, for example, about the ever-growing gaps. But if you've made it up to here, I'm sure you'll be able to fill in those details yourself. Here are a couple of super cool facts that can be shown in the same way. First, even when interpreted as base 2, 3, 4, etc. numbers, Liouville's monster will always be a transcendental number. Second, even when we replace the ones by other digits, we get a transcendental number, as long as infinitely many of these digits are non-zero. Now, adding an integer to a transcendental number gives a number that is still transcendental. Maybe someone will prove this in the comments. So adding 5 to this transcendental number up there gives a new transcendental number, 5.12000 and so on. Here's a fun idea then. Let's take a real number, like pi, and use its digits to create a new number like this. Well, it's super tough to prove that pi is transcendental, whereas proving the transcendence of this weird clone is not any harder than what I've showed you earlier. Okay, next trick. Let's do the same for every real number. What this does is create a clone of the set of real numbers within the set of real numbers that consists entirely of transcendental numbers. Even the clones of the algebraic numbers are transcendental. We just have to be a little bit careful here when we translate a number that features a terminating decimal expansion, like for example the number 1.23. Using that terminating decimal expansion would also result in a clone with a terminating decimal expansion. And any number like this is rational and therefore not transcendental. Of course, that's easily fixed because every number with a terminating decimal expansion has a second decimal expansion with an infinite tail of nines. For example, 1.23 is equal to 1.2299999 and so on. Using this alternative decimal expansion, which features infinitely many non-zero digits, will then give a transcendental clone. Well, one mini problem remains. The number 0 cannot be massaged in this way to give a transcendental number. But okay, as it happens quite often, 0 is a little exception here. Big deal. Anyway, we now got a clone of the real numbers within the real numbers, consisting of transcendental numbers. Of course, since it is a clone, there's a one-to-one correspondence between it and the original set. In other words, just like the real numbers, the clone is an uncountably infinite set. But of course, in addition, all its elements are easy transcendentals. Super cool, right? However, this uncountably infinite set also has the paradoxical property of having measure 0. So although it is as large as the whole set of real numbers, it is so well hidden within that, in a sense, it's not even there. To really be able to appreciate this paradoxical set, you should watch the previous video where I also give a little intro to how you can assign a length or measure to a subset of the real numbers. Or you could head over to Infinite Series, where Kelsey is also discussing these sorts of sets at the moment. I've also prepared a proof of the fact that the clone has measure 0, but I think this video is already getting quite long, and so I'll put this proof on Mathologer too, sometime in the next couple of days. Okay, let's finish here. I hope you all understood and enjoyed this video, but as usual, please let me know what worked for you and what didn't. And if you're struggling with anything, just ask. And that's it for today.